Sketch is a 3D modeling system with a novel gesture-based interface for rapidly constructing and manipulating polygonal models of 3D scenes. Sketch tries to combine the simplicity of pencil sketches with the power of computer-based 3D models. With pencil and paper, it's easy to create images of 3D objects, but they're inherently static. In contrast, it's comparatively difficult to create models on computers, but once created, they're easily manipulated and viewed. Sketch attempts to make computer-based modeling faster and easier by basing all input on drawing and direct manipulation of 3D objects, and also by exploiting user intuition when appropriate. Sketch is intended to be used for prototyping, storyboarding, and communicating conceptual designs of 3D scenes. Sketch requires only a 3-button pointer for virtually all input. The entire interaction dialog occurs directly in the 3D window without menus, buttons, or toolbars. This video was produced on an SGI Reality engine, although it was designed with pen-based systems in mind. This section will briefly outline each of the components of Sketch. Later sections will fill in the details. We begin with an orthographic view of a gridded floor plane. Sketch infers 3D geometry from 2D lines that are drawn in the film plane. This inference mechanism combines concepts from gesture recognition with techniques from 3D reconstruction. In this introductory segment, we rapidly draw a 3D sketch of a dovetail joints in a bed frame. The entire interface for shape construction requires only a single button of a mouse or tablet pen. Sketch supports a large number of primitive shapes, which will be introduced as the video progresses. The gesture that constructs a 3D shape determines its size and its relationship to other objects in the scene. In general, 3D objects are placed in contact with the surface on which they are drawn. We describe this procedure later in more detail. In addition to shape inferencing, Sketch also provides gestural interfaces to standard 3D modeling features like copying and grouping objects, as well as performing constrained transformations. Once the bed is done, we draw the detail of a dovetail joint, much as we might draw it on a piece of paper. Sketch supports schematic elements such as this arrow on the floor plane. Also, Sketch infers CSG subtraction operations from inflections of the drawings. Models can, of course, be interactively manipulated and are subject to default behaviors. Initially, objects are constrained to translate along the surface upon which they are created. However, we can easily sketch different constraints. Default colors are automatically chosen for new shapes to help differentiate them from existing objects. To apply colors and textures, we simply type their name over an object. To make our illustrations more expressive, we support a variety of rendering styles, including a non-photorealistic black and white sketch. Throughout the video, all drawing operations are done with only the first mouse button, all object transformations are performed with only the second, and all camera manipulations with the third. A single modifier key is used for secondary operations like copying colors and drawing schematic elements. The gestures used to create primitive 3D shapes are derived from their salient geometric features. In general, the gestures correspond to contour edges. However, for some shapes, the gestures are related to structural elements. For example, the user can create a cube by drawing 3 visible or hidden edges. Alternatively, the user can draw one edge and then 2 lines to indicate the cube's other dimensions. Notice that as shapes are created, the user's lines are constrained to the 3 principal axes. Some gestures require non-axis aligned lines. This is accomplished by a tearing gesture. We use this tearing technique to indicate a cone. We can create a fountain in the yard by sketching the profile of an object of revolution. The user draws a freehand line segment by pausing slightly before drawing. Notice the profile is drawn in the film plane instead of on an axis-aligned plane. Although less consistent, in practice we found this approach much easier to use. CSG subtraction is inferred automatically based on the direction that lines are drawn. To hollow out the house, notice that the vertical axis of the new cube is drawn down into the base of the house. By quickly clicking on the new cube, we can gesturally delete it and see the effect of the CSG operation. The CSG subtraction technique is used again to hollow out 2 windows and a door. Again, the CSG operation is inferred whenever the user draws a new object through an existing one. The direction of the gestured lines is very important. Some objects, such as tubes, extrudes, and ducts, require a combination of gestures to create them. A roof for the house, for example, is created from 3 extrusions, 2 triangular walls, and the roof itself. To make these objects, we first draw a cross-section by clicking a polyline of possibly non-axis aligned segments with the mouse. The cross-section is followed by an axis of extrusion. We adjust the position of the roof slightly by sliding it with a single axis translation constraint. A walkway to the house is created by drawing another cross-section, but this time we sketch a path of extrusion. Finally, we construct a hose from a cylindrical tap to the fountain. We zoom in and draw a tap. Then we draw a circular profile, a plane normal, and a spine to construct the tube. The scene was completed by adding stairs, a chimney, and window frames. We map textures to some objects by typing texture names like grass, wood, and brick over them. We use a simple wrapping paper-like texture mapping technique that requires no additional user input. This section covers details of how objects are placed in 3D relative to one another. The simplest form of object placement is based on projecting a ray from the film plane through the highest degree or first vertex of the gesture. The cylindrical prop for a three-legged support is inferred to be vertical relative to the floor and is located at the intersection of a ray through the start point of the gesture. Each of the extrusions is placed by sending a ray through the trivalent vertex where the extrusion axis meets the extrusion profile. A cube is placed by sending a ray through the intersection of the three perpendicular lines. We draw a large cylinder for a bullseye target. Then we proceed to draw inscribed cylinders. However, this illustrates that it is often difficult to draw things in the proper position from certain viewpoints, so the user can refine the placement of objects from a more convenient vantage. Another placement technique is used for objects that float in the air, like the dart. First, we draw them subject to the inference that they lie on the floor. To position the dart in the air, we use a modifier key to draw a shadow for the dart. Assuming a directional light perpendicular to the floor, the dart's elevation is inferred from its displacement from its shadow. The dart's height is fine-tuned by translating it along the viewing axis. We also extend some 3D reconstruction techniques by allowing objects to be drawn underneath other objects. We sketch a table by first drawing its top. Notice that Sketch initially places it on the floor. When we draw the first table leg, Sketch detects a T-intersection between the gesture and the tabletop, and automatically infers that the table should be placed on top of the leg. Notice that only the visible portion of the rearmost leg is drawn. Sketch fills in the rest of the leg by extending it upward until it meets the tabletop. We rotate the camera to view the resulting 3D model. To further illustrate the use of T-intersections, we can draw a slide from the table to the floor. Initially, the slide will hover over the table. When we draw each of the two legs to support the slide, they are automatically extended to reach the slide. Finally, to transform objects along the surfaces of other objects, the user can set up contact constraints. To do this, the user draws two perpendicular lines. These are the same two lines that would be drawn for a cube gesture. However, the user manipulates the sphere instead of drawing the third line, so this is interpreted as a contact constraint. A variety of translation and rotation constraints will be seen in the next segment. We end by drawing the shadow for a ball that has bounced off the end of the slide to place the ball in midair. Editing, copying, and grouping mechanisms provide one of the most significant advantages of computer-based sketching over pencil and paper. Here, a user quickly sketches a pair of walls. The user reacts to the sketch and decides to resize each wall by simply sketching back and forth over their edges. CSGs can be edited in a similar way. Here, the user sketches a window opening, then moves it around until they're satisfied. The opening can also be resized. Finally, the user gesturally discards the window cube to see the opening. Once again, we make a window, this time of an irregular shape, and move it around. To sketch a halogen light, the user draws a cylindrical support. Since it's initially too short, they oversketch the stand to lengthen it. To finish the light, we draw a shield and a filament. Notice that during subsequent manipulations, all objects drawn in contact with each other are automatically grouped together. We can also edit objects more dynamically. To create a resizable curtain, we first draw a curtain rod above the window, and then a curtain ring. The curtain ring is placed initially tangent to the rod, so we need to translate it back along the viewing axis to be concentric with the rod. Using a double click, the ends of the curtain are attached to the wall and to the ring. Whenever either attachment point is moved, the curtain automatically resizes to maintain the span. To make a desk, we first make a cube, then cut out an opening for a chair. Next, we subtract a drawer from the desk and draw a single line. Since we drag parallel to this line, it becomes a single-axis translation constraint. Dragging perpendicularly to this line would have yielded a rotation constraint. Constraints in Sketch are limited to tree-like hierarchies and persist until they are overwritten by a different constraint. To illustrate a use of rotational constraints, we will construct a familiar hierarchical linkage. A simplified lasso lamp model is built with 3 rotational constraints, one for each of the top 2 joints and one for the base. Notice, to establish a rotational constraint, the user drags the mouse perpendicular to the axis. All subsequent interactions will rotate the objects in the same way until a new constraint is drawn. To construct a piano with a raised lid, we again use both the CSG subtraction operation and rotation constraints. In this sketch, although we want the piano lid to be lifted, it is much more difficult to draw shapes at arbitrary angles. Instead, we draw the lid initially on an axis-aligned plane in the closed position. This allows us to use the piano base as a guide. To raise the lid, we draw a rotation axis that serves as a hinge, and then drag the lid to the desired position. We now draw a strut that supports the lid. Next, we sketch a music stand. We want the stand to be tilted back, so we draw a rotation constraint for it. After rotating, we determine that the stand is too tall, so we simply resize it and fine-tune its position. To draw the keyboard, we first need to extend the piano base with a long cube. However, it would be cumbersome to have to draw each of the keys one by one. So instead, we'll just draw one key. Then to copy the key, we can just grab the outline of the gesture we used to create it and drag and drop it onto a new position. It would still be a lot of work to replicate all the keys in this way, so instead, we'll draw just enough keys to make a repeatable pattern. To complete the pattern, we first have to change the color of the keys to be white. We do this by typing the word white over the first key and then dragging and dropping this color to each of the other keys. We draw the black keys in the same fashion. Dropping the color in the wrong place is easily corrected. Now that we've made a pattern of keys, we group them by drawing a lasso around them. This group can be copied by translating any one of its components with the shift modifier key. The resulting keyboard doesn't have 88 keys, but we've rapidly created a good approximate model. Finally, to elevate the piano from the floor, we draw a leg up to the piano base. The resulting T intersection once again signals that the piano should be raised to rest on top of the leg. To view the scene, the user manipulates the camera with the third button. By default, the camera pans as the pointer moves. If the user pauses slightly before moving, then horizontal motions will pan the camera, and vertical ones zoom in on the point under the cursor. We now copy the lamp and uniformly scale it by dragging on the outline of the lasso. The filament isn't copied because of a bug in our implementation of extruded objects. Once again, to place the lamp on the desk, we sketch a contact constraint and drag the lamp to the desired position. If the user grabs near the edge of the screen, the camera rotates around the center of the scene. Clicking on an object focuses on that object. This segment shows 4 different rendering techniques in Sketch. The first rendering technique was used in the last segment. In the second rendering mode, we continue to oversketch silhouette and contour edges with multiple jittered lines to give a relaxed feel, but we also turn off all colors to give the scene an even more informal paper and pencil look. By enabling black and white flat shading, we can achieve greater surface perception while maintaining much of the abstractness of pencil drawings. Finally, by shading with faint colors, we can achieve a loose approximation of pastel or watercolor images. In summary, we have presented a system that allows people to quickly realize approximate models of 3D scenes using a gesture-based interface. We feel our approach is even more direct than interfaces which channel interaction through 3D widgets. We envisioned that Sketch could naturally be extended to a variety of other domains, including the specification of animations and interactive behaviors. However, we still would like to support more sophisticated geometry and higher-level control mechanisms, especially for physically based models and articulated figures. Voice input may be useful for specifying non-spatial attributes such as texture and color. It may also prove useful to incorporate a gesture-based undo mechanism and to refine sketch models in conventional modeling systems. We have shown a number of novel techniques, including the ability to graphically repeat operations, to explicitly draw transformation constraints, to select objects with a 3D lasso, and to specify an object's depth by sketching its shadow. We have also demonstrated a variety of non-photorealistic rendering techniques, although there is still much potential for continued work in this area.